Hello, welcome back to Piers Rocks. This Commodore 64 is being powered by Raspberry Pi's RP2350 microcontroller with its 5-volt tolerant GPIOs. Here's the moment last week when I got it working. Let's flash it and see what happens. Erasing, flashing. Yes! It works! I don't know how well this is coming across because obviously it's quite small in the camera that you're looking at, but I'm getting proper character served on this VIC-20 for the first time with one ROM and an RP2350. Success! About 2 months ago I introduced the software-defined retro ROM, which I've since renamed One ROM to be the most flexible ROM replacement for your vintage computer systems. One ROM can replace all of the ROM types in these vintage computer systems. Different models of ROM chips, different sizes of ROM chips, and different configurations of ROM chips. I ended up going with an STM32 based solution because these vintage computer systems tend to run off 5-volt logic internally, and the STM32 was the only microcontroller I could find with onboard 5-volt tolerant GPIOs that had the horsepower for this application. At the time, I really wanted to use Raspberry Pi's RP2350 microcontroller, but I couldn't because there's simply not space on the PCB with this footprint, which is the same size as the original ROM chips, to fit the 22 level shifters that would have been required. 1 month ago, Raspberry Pi announced the new hardware version of their RP2350 chip, the A4 stepping, which has 5-volt tolerant GPIOs. So, I've now developed an RP2350 version of One ROM. In this video, I'm going to cover the process that I went through to come up with the RP2350 version of One ROM. I'm going to cover some of the challenges from laying out the PCB to porting the firmware. I'm going to do a side-by-side price and performance comparison of the RP2350 compared with the STM32 F4 family of microcontrollers. I'm also going to dig into quite a lot of detail on the RP2350 itself, and in particular some of the ways in which I achieve cycle level optimization on the processor. Before I dig into that though, let me show you how one ROM works. This Commodore 64 has sockets for 3 different ROM chips: the basic ROM, the kernel ROM, and the character ROM. And as you can see right now, I've only got a single one ROM installed in this machine with fly leads from the empty sockets. These are from the chip select lines of these empty sockets into the single one ROM instance. This one ROM is being powered by the RP2350 A4 stepping with no GPIO level shifters and is serving all 3 ROMs simultaneously. It's able to do that despite the fact that they're different ROM types. The basic and the kernel ROM are both 8KB 2364 ROM chips with a single chip select line. The character ROM is a 4KB ROM chip, a 2332, with 2 chip select lines. Of course, if you want to, you can install 3 one ROMs in this, or a mix of original ROMs and a one ROM in different ROM sockets. One ROM can also store multiple ROM images, which you switch either at boot time or dynamically at runtime using the onboard jumpers. You can even use one ROM to instrument your retro equipment. Here's a graph showing the number of ROM accesses per second for the 3 different ROMs in a Commodore 64. At the heart of one ROM is the firmware and a hand-rolled, cycle-optimized main assembly loop that's spinning round, detecting chip select line going active, retrieving the byte to serve from a RAM lookup table and getting it applied to the data lines just as quickly as it possibly can. Because both the STM and the RP microcontrollers are ARM Cortex based, right now the firmware is very similar between the 2 devices. However, the PCB layout is quite a bit different. Let's look at that now. Before I actually go into the details of PCB design and the challenges that I faced, it's worth talking about some of the design goals for one ROM. Here I've got one ROM next to one of the original ROM chips that one ROM is designed to replace. And one of the key goals was to fit in the same footprint of the socket for one of these original ROM chips. So that constrained me greatly in terms of all of my design and layout choices, both for the STM and the RP variants of the board. I always intended one ROM to be a 2-layer PCB for cost reasons, and also to restrict components to a single side of the PCB, the top of the PCB, again for cost reasons. Originally, I wanted one ROM to be hand solderable. Now, hand solderable is a subjective thing, right? For me, the STM32 microcontroller I'm using and down to 0402 components is just about hand solderable. But other people, it's not going to be hand solderable. And to be honest, most people using one ROM are going to get them fabbed using an assembly service like JLC's assembly service. I also want one ROM to be flexible. So that means including a whole bunch of additional pins, both for programming on the fly, so you can reprogram one ROM while it's installed in the host system, but also for things like selecting different images at boot and at runtime, and also potentially using one ROM to have other cables connected to the host system driving reset lines, and so on. We take a look at what's in front of us now. We've got two PCBs. On the left-hand side here, we have the STM32 variant of one ROM. And on the right-hand side here, we have the RP variant of one ROM. Down the left-hand side and the right-hand side of each board, we have the pins that go into the existing host ROM socket. At the bottom here, we have programming pins on both boards. And at the top, we have a bunch of expansion pins on both boards. When you take away all of those pins, you're left with around about 17 by 14 millimeters, or about a third of a square inch of area to fit all of your components onto. On the face of it, the STM32 board actually looks quite challenging to fit everything in, because the STM microcontroller I had to go for was a 64 pin variant. I've chosen the LQFP package, which has the legs sticking out of the side of the package, so it's vaguely hand solderable. And you can see it's really large. It almost comes to the pins on either side of the PCB. But the STM32 has a great advantage in that there's no ground pad underneath it. So I can break all of the pins out from the STM32 underneath the STM, then drop them down to the underside of the board with vias, and then route them to where they're needed. The RP2350 is another matter entirely. So this is the RP2350 footprint, and you can see it's tiny compared to the STM32. The STM32 with its legs is about 14 by 14 millimeters. The RP2350 is, I think, 7 millimeters by 7 millimeters, but there's two big problems with routing the RP2350 on such a small two-layer PCB. One is the ground pad here takes up the majority of the underside of the RP2350. The second is that the recommended hardware design for the 2350, which I stuck with as rigorously as I possibly could, has this ring here, which is the core voltage of the RP2350, 1.1 volts typically, which I'm going to come back to quite a lot in this video. And it also has the 3.3 volt power rail for the microcontroller underneath. So you're out of luck in routing traces on the top side of the PCB with an RP2350 board. What you have to do is you have to go outside the chip with your traces, and if you need to drop them through the board, drop them to the underside and route them to where they need to go. It's worse than that though, because the design recommendation for the RP2350 is to have 9 stitching vias through your ground pad to the underside of the PCB to help with heat dissipation. If you do that on this board, you've basically not got enough room to route your traces. We'll look at the underside of the board in a second, but one of the trade-offs I had to make with this design was to go with fewer stitching vias than recommended for this. Now I'm hoping that's okay, because one ROM really doesn't use a whole host of peripherals on the RP2350, and while overclocking is possible, and I'll show you that later on in the video, I don't think that this usage of the RP2050 is going to dissipate too much heat for this board to actually be able to get away. But it was one of the trade-offs I had to make to use the RP2350 on this board. Now you might be sitting there and saying, well Piers, why didn't you just go to a 4-layer PCB? They're not really that much more expensive. I don't think a 4-layer PCB would actually have made any difference really, because my 2 additional layers would have been taken up by the ground and power planes. I wouldn't be able to use the top side for routing traces under the chip because of the ground pad. And I still wouldn't be able to use most of the underside because I'd have these stitching vias all the way through the board. So I think actually to make this easy or easier, you'd have to go to a 6-layer PCB and the additional expense associated with that. Now, I've never laid out a 4-layer PCB, let alone a 6-layer PCB, so I might be wrong there. I'm not a hardware engineer, I'm a software guy. As well as the RP2350, all of the pins, there are really 4 sections of the circuit board we need to look at with an RP2350 design. And that's the main voltage regulator that steps down 5 volts to 3.3 volts on the board. So the ROM is powered with 5 volts from the host system. That's this section of the PCB. And on the STM, it's over here. I'm using the same part, the AP2112, which is, I think, a SOT223 size component. So it's pretty damn small, even though it looks large on the screen. The next section is the flash. So the RP2350 uses external flash. Yes, I know there's variants that have flash built in, but firstly, the availability of them is quite poor, particularly on places like JLC. And secondly, I'm not sure that the A4 stepping and the 5-volt tolerant GPIOs actually extends to those parts with the flash built in. So I had to go with a separate flash chip. And again, I've gone for a very small surface mount flash chip on this PCB. There's the oscillator circuit down here, and frankly this is massive when you're trying to lay out a board as small as this one. I'm using Raspberry Pi's recommended oscillator for this design. And then the 4th section is supporting circuitry for the internal core voltage regulator for the RP2350. So the RP2350 contains the voltage regulator that steps down the 3.3 volts to the 1.1 volts that the core needs. But you have to provide some external circuitry to enable that internal voltage regulator. You've got an inductor here and a bunch of different capacitors. And while it doesn't sound very much, it uses up a significant amount of real estate on this board. I'll come back to talk more about that in a second. But when we compare all of these external components with the STM32 variant, yes, we've got the voltage regulator to step 5 volts down to 3.3 volts. But there's no external flash. The STM32 has flash built in. There's no oscillator. The internal oscillator on the STM32 is really quite capable and more than enough for this application. The internal oscillator on the RP2350, well, I think it would be unfair to call it crap, to be honest. I just don't think it was ever designed to be used in anger. I think it's just designed to be used to boot up to the system to the point where it can access the flash, load some firmware, and then switch over to an external crystal. But there's no external crystal required on the STM32, no external flash. And while there is a very small amount of circuitry required for the internal core voltage regulator, it's like 2 0402 caps. Now I've got all of these sections laid out. Let's talk about the internal voltage regulator a bit more on the RP2350. And if you read the hardware design for the RP2350, which gives you a recommended layout, there's dire warnings about laying out this circuit basically exactly as I have it here to get the best possible performance. I've looked at other commercial designs using the RP2350 and they don't seem to stick particularly carefully to this. Maybe they predated the hardware reference design from Raspberry Pi. But what you have essentially is you have a bunch of pins coming out of the RP2350 that then access this external circuitry to create your 1.1 volt core voltage reference. That then gets fed back in to this pin on the RP2350, which is one of the 4 pins that requires the 1.1 volts. There's also a massive trace, relatively, on the underside that goes down to here, I think it is, this via, and then feeds this 1.1 ring around the ground pad. And then it gets tapped to a number of different points on the underside, coming through with vias, and then fed back into the chip itself. I don't know, can't remember precisely, but I think it's those pins that you have to feed 1.1 volts back into. So keep that in your head, because that's real estate that's used on the underside of the circuit board that I will not be able to route traces through. Now you might be saying, well, Piers, couldn't you have made those traces on the underside shorter by breaking the vias out much closer? Well, no. Partly because you've still got to get the other traces out of the RP2350's pads, but also because you also have to have bypass capacitors on each of these 1.1 rails going into the RP2350, and if you put those too close to the chip, you're just simply not going to break out your other traces. So I've tended to put the capacitors a reasonable distance out from the RP2350 so that I can get the traces out, but not so far that I can't route traces on the underside. So let's now take a look at the underside of the PCBs. On the left here, this is the STM32, and you can see all the vias underneath the STM32 where I've dropped traces through. And then it's actually pretty easy. I mean, it took a while to get this layout as neat as this, but it was relatively straightforward to get all the traces to all of the pins. On the right-hand side, we have the RP2350 sitting here on the circuit board. Now, the way I've done this is it's as if you've turned the PCBs over. I've not mirrored it, so it's as if you're looking through. It's as if you turned them over. So things that were on the right-hand side when we were looking at them before are now on the left-hand side. So the voltage regulator circuitry is round about here on the RP2350 board. And here's the big fat trace that brings the 1.1 volts that the voltage regulator in the RP2350 has created, brings it to that ring around the ground pad, and then gets tapped out. So I think you can see at this point just how challenging that makes it for routing traces on the underside of the PCB. I think I did a pretty good job of figuring out which GPIOs to use to attach to which pins of my ROM based on what would be the easiest to route. Yet I still had this, about 8 traces to get from one side of the board to the other. The only way that I could do that, using 6mm traces and 6mm distance between the traces, which is the minimum that the cheap PCB fab services will let you go to, was to route directly underneath the RP2350, and therefore do away with most of the ground stitching vias. These are the 2 ground stitching vias that I managed to stick with. Now at this point, I suspect there's people like furiously banging into their keyboards in the comments section. In fact, I can almost hear them already saying how this design is going to create a whole bunch of noise because I have these traces going underneath the RP2350. What do you want me to do? As I said, I don't think going to a 4-layer PCB will really help. I mean, it might suppress noise a little bit, but to actually make routing easier and to give me more space for routing, I think I need to move to a 6-layer PCB, and I don't want to do that for this design. But for all those people who are still furiously banging away at the keyboard and telling me what to do, all the designs here are open source, so feel free to go in and have a go yourself, or make constructive suggestions to me down in the comments about how I can do things better. Please, I'm all ears. To talk about the firmware for the RP2350 version of ROM, I'm actually going to have the schematic up in front of us. So the STM version of ROM is a completely bare metal C and assembly application, directly reading and writing to the STM32's hardware registers. For my porting to RP2350, I took exactly the same approach with the RP2350. So I'm not using the SDK, I'm directly accessing the hardware registers of the device and spent quite a few hours pouring backwards and forwards through the datasheet trying to identify exactly what I had to do and which registers I had to access. And of course I did look at some of the SDK code to see what it was doing. But one of the most important things about the firmware is actually the optimizations to allow us to serve ROMs as quickly as these systems need us to serve ROMs, and choosing the right sets of pins to use for which lines is really important to, where possible, avoid cycles, to avoid masking and shifting instructions in particular. On both the STM32 and the RP2350 designs, I managed to avoid essentially all but one mask operation, and I avoid all shift operations when I'm reading in, doing anything with GPIOs and writing them out again. And the way I've done that is with a couple of different tricks. First thing I've done is I have assigned the address lines to ports 0 to 15 on the RP2350. The chip select lines are mixed in with the address lines, and they're all jumbled up to make routing easier, but that's fine. I can sort that out in pre-processing the ROM images before they get written into firmware, and then when serving the images out. That's all fine. On the RP2350, reading the GPIOs is a 32-bit operation. There's a 32-bit register that contains the state of all of the different GPIOs. So on the face of it, I have to read in a 32-bit register, and then I have to mask out the top 16 bits before I can use that address and CS lines. I use that as an offset into a table in RAM that contains the ROM bytes to serve, selects the right byte, and then writes them out. I can actually use an assembly instruction, a half-word load assembly instruction, so that I only load in the bottom 16 bits of the GPIO register with a GPIO state. That means I don't have to do any masking of the bits. I've got a 16-bit offset, so that I can use that as an offset into a 64 kilobyte ROM table in RAM. And by some funky pre-processing, I can get any of the different ROM images that I need for any of the different size ROMs properly mapped into that 64 kilobyte table. The other thing I'm doing, and I'm prouder of this technique on the RP2350 than I am of the address technique, is I'm using lines 16 through to 23 for the data lines. So I've now read a byte from RAM, so I have a byte of data sitting in one of the Cortex processor's hardware registers. How am I going to write that out to bits 16 through 23 without any kind of shift or mask operation at all? Well, the SIOs, the single cycle IO instructions for reading from and writing to GPIOs in the RP2350 do not, well, they sort of claim that they don't support byte and half word writes. But then they say if you do an 8-bit or 16-bit write to one of the 32-bit GPIO registers, then the byte or the 2 bytes that you write get replicated to the rest of the word before they get written to the GPIO register. So I've got this byte in my hand, which is bits 0 to 7, that's what a byte is. If I write that byte to the out register via the SIO, the hardware automatically replicates that across the word, so I get 4 copies of it in each byte. The only GPIOs that are outputs are the data lines in pins 16 to 23, so they get the right value and nothing else gets affected. So that's how I do away without actually doing any shift operation at all. Now I'll come on later in this video in a very detailed section to some other techniques you can use to access the GPIO registers on the RP2350. I think this is the fastest way of doing it on this hardware, and I think that might be faster than using PIOs or using the GPIO coprocessor, which I'll talk about later. Now, when I actually lied when I said that there were no other pins were output pins. There is one other output pin on the RP2350 in this configuration. I'm using pin 26 to drive a status LED on the device. And I, by default, turn that LED on when one ROM is ready to start serving bytes. Using this technique of writing a byte of data to the output GPIO output register and getting it replicated actually means that the LED is flickering based on one of the bits of one of the data lines is getting replicated and applied to the status LED. So I'm applying some level of PWM to the status LED, but this is being driven at a megahertz, so you're not really going to notice any flickering with your eye, but it might be slightly dimmer than normal if a lot of zeros are being, if a lot of ones are being written out of that particular data line. The only other thing I want to say about the schematic and the PCB layout is that I wasn't able to route quite all the pins that I wanted to route. I did want to route GPIOs 24 and 25 to a couple of the jumpers that are exposed on the PCB. And while I did manage to get some of the lines routed to the jumpers, I couldn't get these two routed. So there's currently 2 unused GPIOs on the RP2350. I have an idea in my head about how I might actually be able to change the layout of this PCB and be able to route those traces as well, but that's unlikely to be a quick thing, so I'm probably going to have to rip up my entire routing design and start again. Let's talk about price.
One of the things that people have made a lot of noise about since the RP2350 announced 5-volt tolerant GPIOs is how much cheaper the RP2350 is than an STM32 microcontroller. And it kind of is cheaper, but it's not as simple as that. On the screen now, you're seeing a price comparison from a couple of days ago from lcsc.com. That's JLC's parts website. I'm not sponsored by JLC, just to be clear. I just like their services. And all of the prices I'm going to talk about here are in quantities of one, or if the minimum quantity is higher than that, whatever the minimum quantity is, what the prorated cost of a part is at that value. So the RP2350 was showing us $1.74. The STM32F411 RET6, which is a perfectly fine microcontroller for doing the one ROM job, was $2.69. So the RP2350 is 35% cheaper. Hooray! Let's go with that. But do you remember all those extra components that we had to stick on the circuit board? We needed the additional voltage regulator components, we needed external flash, and we needed an additional oscillator. Once you factor those in, the RP2350 is more expensive than the STM32. It's basically $3 compared to the $2.70 for the STM32 microcontroller. So the RP2350 is not cheaper than an STM32F4 microcontroller, at least not the one that I chose to compare it with here. Now again, people will be banging away furiously into their keyboards saying, I can't get microcontrollers for this cheap. Well, you need to buy them from LCSC and then you can get them this cheap. There'll also be people banging away saying, well, it's not a fair comparison. Your RP2350 has 2 cores and it has far more RAM, and it has your external flash has far more flash capability than the STM32F4. Yes, that's all true. Maybe this isn't a particularly fair comparison, but if you're just looking at microcontrollers that get the job done, you can do it cheaper with an STM32F4 microcontroller. Now, does that mean that I'm recommending people stick with an STM32F4 microcontroller? You probably want to watch the rest of this video before making any decisions, because there are some other details that I'll go into that are interesting. Alright, so RP2350 is $3 compared to the STM32F411 at $2.70. It's actually worse than that when you get small quantities of PCBs fabbed. So JLC PCB have different types of parts on their list. They have basic parts that you pay what the price of the part is, and basically that's it to have your board assembled. And then there's extended parts, where I assume somebody actually has to go and get a cartridge with those components in, plug them into the pick and place machine for your assembly, and that costs you $3 for every unique additional extended part that you use. Guess what? All of the Raspberry Pi recommended additional components are extended parts. Now, at least they are extended parts and not some like advanced part that really pushes you up the price bracket. You pay $3 extra for each of these different additional parts. So that's an extra $9 for your total assembly price for an RP2350 board compared to an STM32F411 board. So how much are you looking at to have RP2350 variants of one ROM assembled by JLC? Well, I got these 5 RP2350 boards fabbed for $44 a week ago. That's about $9 per one ROM. If I'd had 20 fabbed, it would have cost me about half that, about $4.45, $4.50. This is all plus tax, plus shipping. If I was selling them, bought 100 say, they'd cost me $3.20. Obviously, STM32F4 versions would also come down in price quantity as well. At the same time as having these RP2350 boards fabbed, I had 5 STM32 F411 boards fabbed, and they cost me about $32 compared to the $44. But when you're building them in quantity, they're going to be roughly the same price. And if you were comparing them with a more advanced F411 STM microcontroller, the RP2350s are cheaper. Let's talk about GPIO 5-volt tolerance on the RP2350. And it is 5-volt tolerant, right? It's running in this Commodore 64 behind me. There's no level shifters. I can't fit them on the PCB. To check this out, we have to look at the datasheet and the I/O electrical characteristics section. And if we look down here, we can see the input voltage that is accepted on the 5-volt tolerant GPIOs. Now that's pins 0 to 25. So the ADC pins are not 5-volt tolerant, so don't stick 5 volts into those. That's one of the reasons I kept my ROM pins down to 0 to 23 on the board, and also I'm prepared to use 24 and 25 and break those out, because they're the 5-volt tolerant pins. You're tolerant up to 5.5 volts. Great, hurrah. Just beware. These retro systems have old and potentially failing voltage regulators in them. I've seen the voltage regulators on some of my retro systems hit 5.5 volts, and I suspect on some people's systems they go higher than that. The original ICs in some of these systems were rated up to a maximum absolute voltage of 7 volts on their pins. And the STM32F4 microcontroller is rated up to a whopping 7.3 volts on its pins. So there is some risk when using an RP2350 in a retro system running off 5-volt logic that your aging voltage regulator will be failing and will be outputting a voltage that's too high and fry your RP2350. Now, just in case you think I'm being a bit of a fearmonger here, and I was showing you the I/O tolerances and that, yeah, it would be fine above that, it just might not work correctly, but you wouldn't fry the chip. This is the section in the datasheet that talks about absolute maximum voltage. And for the 5-volt tolerant GPIOs, we have an absolute maximum voltage of 5.5 volts. So, for most cases, this should be absolutely fine. If you've got a well-behaved bit of equipment, you're putting the RP2350 in, you'll be fine. But there are some cases, if you've got some very old equipment with very dodgy voltage regulators, you may be better off with an STM32 or other microcontroller with 5-volt tolerance other than the RP2350. I don't know how much headroom Raspberry Pi have built into these numbers. Now we're going to look at performance comparisons between the RP2350 and the STM32. And for these tests, we're going to clock the STM32 at 150 megahertz and the RP2350 at the same 150 megahertz. So I'm using an F405 that's maximum clock speed is 168 for this test, but it's clocked to 150. And the way I'm actually going to measure the startup time is going to vary slightly between the two chips, but it is measuring the same thing. On the scope here, at the top, we have a clock output from the F405. And this is showing 30 megahertz because the clock is being divided by 5 before its output, so my baby little Rigol can actually cope with the frequency. And then down here I have the output of the 5 volt to 3.3 volt voltage regulator. And we're going to trigger off this power line. When 3.3 volts starts coming out of the voltage regulator, that's when we're going to start the clock and time the startup time from there. So my firmware, the STM32 firmware, starts this clock output if it's configured just before entering main loop. So that's going to be our startup time. Power being applied to the microcontroller to my main loop starting to execute. Now, the power line isn't, I think, really that noisy. It's just my oscilloscope setup isn't optimal. So let's see how long the STM32F405 takes to start up. Well, that was pretty quick. 1.5 milliseconds. So again, this is from power being applied, 3.3 volts, to the clock starting, which this clock output is started just before entering the main loop. So 1.5 milliseconds, that includes the processor coming out of reset, running my setup code, and entering the main loop. So to measure RP2350 startup speed, I'm actually going to be measuring the output of the GPIO that's driving the status LED. And if you remember earlier, I said that actually this is getting data applied to it as well. We can see that on the top line of the oscilloscope. The status LED is configured to be an output low just before starting the main loop. So if we look to when the status LED first goes low, that's the equivalent startup time compared to the STM32. And again, I'm clocking the RP2350 here at 150 megahertz. So I'll power on the C64. And let's have a look how long that took. So that startup time took about 17 milliseconds. It takes about 10 milliseconds for the status LED to be driven at all. I think this is the time that the RP2350 is taking to come out of reset. And then it's taking another 7 milliseconds before the status LED goes low. Now the behaviour between the two firmwares is very, very similar. So I suspect that most of this 7 milliseconds is not spent in my firmware, but is actually being spent in the RP2350's onboard bootloader. Maybe wrong about this, but side-by-side comparison, to get into my main loop on the RP2350 is taking 17 milliseconds compared to 1.5 milliseconds on the STM32F405. So that's an order of magnitude slower. Now, I know you're going to want to see me overclock this RP2350. I've currently got it in as the character ROM in this Commodore 64, and it's in boot cell mode waiting for firmware. So I'm just going to flash firmware that's going to overclock it to 540 megahertz. Yeah, I could nickel and dime you. I could go all the way up from 150 to 540, but you want the money shot, right? This is building the firmware, and it's now erasing the device and flashing the device, and boom, that RP2350 is now running at 540 megahertz and serving the Commodore 64's character ROM. I should probably add to that overclocking segment that there was nothing stopping me at 540 megahertz except me and wanting to save my silicon. I had the core voltage of the RP2350 up to 1.6 volts to run at 540 megahertz, and it seemed reasonably stable there. Maybe I should have pushed it just a little bit higher at that clock speed, but the internal voltage regulator can be stepped much higher up than 1.6 volts, although you are doing it at your own risk. If you are overclocking your RP2350, I definitely recommend investing in a small heatsink for the IC. I'm going to start bringing this video to a close now. There's plenty more I could talk about. Lots of stuff I learned about the RP2350 as part of this process. I tried out the XIP cache pinning functionality, which is supposed to let you preload and keep cached your instructions in flash so that you're guaranteed to have them accessible without any wait states. Whenever I tried using that functionality, I either locked the core up or I faulted the core, so I don't know what's wrong with that. I tried using the GPIO coprocessor support on the RP2350. This is a direct connection between the ARM Cortex core and the GPIO subsystem of the device that doesn't go via the standard bus matrix like the SIO instructions do. And therefore, if you've got bus contention, it's a quicker way of accessing the peripheral. I tried that, and actually it was no faster, and it would seem to be just marginally slower for me. Might be because I don't have a particularly contended bus, but going direct to the hardware using the coprocessor provided no benefit whatsoever. There's bound to be people asking questions about why I'm not using the PIOs. Did I use the PIOs? What did I find out about the PIOs? I've not yet used the PIOs. I'm sure I will try the PIOs. I'm not at all convinced that PIOs are going to be faster for my application, given how optimized I have the main assembly loop. And given my PCB layout and GPIO assignment, the fact I've managed to get rid of data shifts and data masks for this application, I don't think I'd be able to use the same techniques with PIOs. I would be able to offload some of the processing to PIOs, but I don't think it would make the overall getting a byte served faster. It might make it more stable, more deterministic, although it's not going to be entirely deterministic because there's still going to have to be loops in the CPU to pull bytes out of RAM. Anyway, if you want to find out more about the technical gory details, and in particular go into more depth on things like price comparison, PCB design, performance comparison, and so on, there's a technical blog post that I've released in parallel with this video, linked down in the description. If you've got any questions about how I found working with the RP2350, why I made the decisions that I did, stick them down in the comments. I'll do my best to answer. If you've got any suggestions for me, any ways you think I could implement one ROM better on the RP2350, I'm all ears. Please stick them down in the comments and I'll take a look at them. I hope you found this video interesting and useful. If you did, please do consider sticking around. It's highly likely to involve microcontrollers, retro systems, or both, and also deep technical content. So until then, rock on.